We've been told that gravity is a force.
Gravitational force.
The force of gravity.
Gravity is among the fundamental forces.
But, spoiler alert, it's not. This video will tell you the truth. In only 9 minutes you'll become a gravity expert. So you can impress all your friends, whether they are 5-year-olds, YouTube science enjoyers or theoretical physicists like me. So, let's find out what gravity actually is. Gravity happens when you drop your phone and crush your screen, or when your foot makes the wrong step at the wrong time and you crush your bones. And all that thanks to Newton, who once said, "All things must fall down, because all things attract or pull on one another." Well, thanks for that. But of course we know it's better this way. Without gravity we would be floating through space, because down is wherever Earth is. So we just happen to be on Earth's surface because we are falling down. And we are falling down because all things pull on one another. Well, actually Newton said all masses attract one another. So all things that have a mass, and that's basically all things. So all things fall down because all things attract one another due to their masses. The bigger the masses, the bigger the attraction. The greater the distance, the weaker the attraction. Actually a lot weaker. This gives us Newton's gravitational law. This here is just a number that tells us how strong gravity is compared to other forces. Ah, forces? What's that? The observant and self-questioning viewer may wonder. A force makes something move differently, slower or faster, or into a different direction. Ultimately, it can stop things or make them move in the first place. Just like you can get this channel moving. So, please subscribe and like if you'd like to. The moment you let go of your phone, the mass of the Earth pulls on the mass of your phone. This gravitational pull makes it fall faster and faster. Gravity is accelerating your phone until it crashes into the ground. So forces are about accelerating things. And in the case of gravity, this acceleration points downward, where down means toward the greatest mass, because the pull of the greatest mass outweighs that of smaller ones. Great! Quite impressive to a 5-year-old. We can use this theory to calculate a lot, like how long your phone takes to reach the ground. But if we had stuck to this theory, we would not have modern planes or GPS today. If you ask Google Maps where you are, it would be off by kilometers. No! That's because Newton's theory isn't quite right. I break that down in this video. The key is that Einstein once asked, "How do you know that you are falling towards Earth and not Earth towards you?" That takes us to the next level. To explain it, let me turn off gravity. I could put you into space. In space you're weightless. You're just floating around. You feel no gravity. Or I could put you into a 0G airplane. A plane that falls so fast you feel weightless. Or I could put you into an elevator. An elevator that falls down. During the fall you feel as weightless as you'd feel in space. Actually, you can't tell whether you're in space or free falling on Earth. If the space elevator now starts to move, you would stop floating. That's similar to a car starting, where you get pushed back into your seat. In the accelerating elevator, you would simply stand on the ground. And if you have a really bad short-term memory, you would start to think that you're in a non-moving elevator on Earth. Inside the elevator, you can't know if you're in a gravitational field or just in an elevator that speeds up. So, what if the Earth is just an elevator accelerating through space? Then we are indeed floating through space and no gravity pulls us anywhere. But the Earth moves towards us. It pushes us forward, just like the space elevator pushes us upward. Then we need no force to explain why you're standing on Earth's ground. And that's why gravity is no real force. Otherwise we could not turn it off or confuse it with an accelerating elevator. But hold on, Einstein, the attentive and critical viewer says. If the Earth is my elevator that moves me through space, what about the millions of other people who don't stand where I stand? What about my best friend? Are they just falling off like someone underneath the elevator falls off? No! This was indeed a troubling question for Einstein, but he he came up with the following answer. While floating through space, we always float in such a way that we land on the ground of the elevator and never underneath it. And I call this the curvature of spacetime.
What?
We don't have to understand spacetime to get what's going on here. Let's imagine you and your best friend are standing somewhere on a surface. And let's imagine you are lazy. You don't want to waste energy. So once you're moving one way, you'll just keep going. You won't turn, speed up, or slow down. We remember, this is something a force would have to do for us. Imagine you and your best friends are both headed straight towards north. Cause someone told you north is where the cool kids are. So you're both walking on straight path and you never turn. At some point you think, I wish I could meet my best friend, but I won't change my way. I'm too lazy. Universe, please help me. The universe says, yeah, why not? And the surface you're walking on starts to bend until it becomes a ball. If you're both walking straight north on a round ball, you will eventually meet at the North Pole. And none of you needed to change course for that. None of you even realized that you were not on straight parallel lines. We only see curved lines if we zoom out. And now imagine this curved surface is the medium our whole universe sits in and moves through. This medium isn't round, but it has bumps and dips. This medium is not three-dimensional like the ball, but four-dimensional. But don't worry about that. Just keep this analogy in mind. Whether a path looks straight or curved depends on your perspective. Whether you meet or don't meet depends on the shape of the medium you're on. Hold on, the attentive and well-educated viewer says. I've seen this before. This medium is what we call spacetime. Great! Now, let's get to the level that can impress theoretical physicists. Actually, not only you and your best friend are lazy, but everything in the universe is lazy. Every planet, every star. They would never speed up, slow down, or change their way by themselves. They stick to one direction and keep a steady speed. From their perspective, they are moving on straight lines. Those lines are called geodesics. The path something takes if it does not use any energy. Being on a geodesic always feels like moving continuously along a straight line, or not moving at all. But from the outside, a geodesic can look completely different. It can look like an orbit or as if something is falling to the ground. And all just because spacetime has some kind of weird shape. Why? Well, Newton was not completely off when he was talking about masses creating gravity. Everything not only moves through spacetime, but also deforms spacetime. The bigger the mass of a thing, the greater the deformation. That sounds familiar. The bigger the masses, the bigger the attraction. Newton's theory and Einstein's theory are actually somehow connected. Big things like planets shape spacetime more intensely. Shaping spacetime means shaping geodesics, and suddenly a geodesic can point directly onto a planet or orbit around it. And to us it looks like there's some kind of force at work. But in Newton's theory, this only works on masses. In reality, however, the shape of spacetime affects everything. Also the one thing that has no mass. Light. Light rays get bent by the curvature of spacetime. Leave me a comment if you want to learn more about this. So, our ways, the ways of light rays, every path is affected by the shape of spacetime. And heavy stuff like planets, stars, or the elevator curve spacetime. That's why we always float in such a way that we land on the ground of the elevator and never underneath it. So, if you drop your phone, don't say stupid gravity, say stupid curvature of space-time. And if a theoretical physicist drops their phone and says gravity is my least favorite force, suggest that you could turn off gravity for them, and then brag about how this is the reason why gravity is not a real force. Because actual forces can't be turned off just by letting an elevator fall down. But why do we still teach gravity as a force? Because this scientific model works quite well, but it goes wrong sometimes. To answer when and why, you need to understand how Newton's and Einstein's model fit together. Find out in this video. Thanks for watching. Please drop your questions in the comments and subscribe to find out how it actually works.